on flow chemistry and the manufacturing of organic molecules. Flow chemistry is an alternative to the traditional batch reactions that had previously been used in pharmaceutical and productions. In this method, the reaction occurs inside a tube or a pipe with a continuous flow of reagents. So you're able to modify them based on automated valves and computer controls that can make real-time assessments of the reactions that are occurring to have the most efficient product output. You can see that in the flow chart. There's many different ways that you can modify what reagents are present in the reaction, and those are represented by those black bold T marks. The benefits of flow chemistry are that it is potentially safer for those hazardous reactions because it is a completely enclosed system. You have better control over the reaction, and because it's automated, you have higher reproducibility and better outputs from this method. You also have a higher output for a smaller reactor, which is very beneficial. I was interested in this topic because in 2022, a very small version called the Cube Lab was launched at the International Space Station. It was developed by Boston University's Beeler Research Group, and this could potentially lead to the manufacturing and assessment of pharmaceuticals or inorganic molecules in microgravity, which could potentially expand all of the potential outreach for space. And you could, in space travel, space applications, this could really provide a very versatile tool if this were able to be successful. The research hasn't been released yet as to whether or not, but it is very exciting to know that it's happening. This method was discovered in the 1950s. That was when the first patents appear. It was initially a very cost-prohibitive machine, and the FDA labeled it inefficient. However, perception changed as the machines developed, and companies realized that there was a reduced cost because there were smaller machine footprints, and because you had that high level of control of solvents, you had less waste, which was financially beneficial. There also was a shift from multifunctional chemistry reactors to specialized product lines where you don't need to make many different things, you need to make a lot of one, and that is where the flow chemistry set really shines. And they also had increased success in producing APIs to expected standards. So this is really relevant to what we've learned in one case for Grignard reagents. Because you're using a flow chemistry reactor, you can modify how much of the Grignard reagent is present in a reaction, which can drastically change your output that you wouldn't necessarily have the same control over if you were using a batch set. As I mentioned, you can in real time produce the reagent and use it in the system, which leads to a high level of control. It also is very beneficial for reactions like hydrogenation because the reaction is conducted in a tube, which is very easy to manage the thermodynamics of. So for this highly exothermic reaction, you can manage that by insulators or heat sinks within the machine. You also have higher control of flow rates and pressures, which is extremely beneficial. So this is a really neat process, and it's a very effective process that we see developing. And I myself didn't know that it was so highly used in pharmaceutical production, but it was very interesting to learn about. Here are my citations, and thanks for listening.